Right. So applying the same principle to the moving coil. So this torque will be equal to, as a constant times the angle of twist. So the angle of twist can give a measure of the current flowing through. This is a constant that we know. We can work out this. Then we can find the angle of twist. The angle of twist will be proportional to the current that is flowing. Okay, from here. If you make it I will be proportional to what? All these being constant, I will be proportional to what? This. And this work out. So this is the for the those that are used for measuring current, okay? To measure current, okay? Right. The device for measuring current. This principle will work. Alright. Let's look at what we call Hall effect. The Hall effect, okay? Hall effect, let's say we have this conductor. It has current in it, it's moving, and then there's another field set up around it, okay? The magnetic field, okay? Right, at 90 degrees, okay? So far as we have, this is current conductor, okay? If it's moving through a field, and then this field is also varying, okay? There will be a second kind of EMF that will be set up. The electrons will be separated. So you have electrons going here, negative, and then have positive sign here. So negative, positive sign. So this separation for a current conductor in a field that has a magnetic field changing around it. This effect is what we call the Hall's effect. The Hall's effect. Okay? Can be measured or calculated from the principle that EMF setup is proportional to the rate of change of flux. The rate of change of flux. Okay, this is E. Of course, this E should be equal to K. It's negative because it's decreasing. Okay, because what is formed has a limit. Okay, K d∅ over dt. Now this works for the force which is below and alpha, where K is equal to 1. This works for it when K is equal to 1. So we can say that A is equal to negative phi dt. This equation is very important. You can keep it. Okay, so this is the Hall effect. So in essence, we are saying that when you have a conductor, so far as you have a conductor, this is a conductor. Let's say another magnetic field acting maybe perpendicular to it. Okay, if it is perpendicular to it, will set up EMF in this one. So 90 degrees, it will set up another EMF in this one. Okay, of course, once it's EMF set up by a changing field, the EMF will try to oppose set up a kind of force to oppose the change that is causing it. Okay, that's why we call this the back EMF. Okay, so that's the relationship. Right, so this will bring us to the end of the Hall's effect. Then we have, we should look at Lenz's law. We'll look at these ones. Yeah, so what I said was the magnetic flux, okay, which is B. So what is this? It's given by 1 cos theta. Okay. So here there's no current in there because we are talking about flux. That's the magnet position, so there's no current in there. But the force or the beta for a current conductor, the force or the beta for a current conductor is proportional to the sine. Okay, let's say funny sine alpha. Okay. But remember, this sign can also be replaced by cos theta, where these two are complements. Okay, that's the principle. That's what I want to. So this is for magnets. Okay, and this is for a current conductor. That's the relationship. Okay, right. So and of course you can use Barney comes in when we are talking about this force has become torque. Okay, has become torque. Okay, but this force and beta, they are also linked to I del sine alpha. Okay, that's what I mean. Of course, torque, we'll be looking at the actual, once it is rotating, it's a body rotating about its axis, then it's about rotation. Rotational force is what we call torque. So, but because it's a couple kind of torque, then you would have the distance from the point, the midpoint being the diameter. Okay, all right, so that is that. So this point has been made. Right. Let's look at this as a transformer. So we have the primary side here, this is the secondary side, okay? So current comes, now because this current is going around, it is changing, the magnetic field is changing. So it will induce current in this one. Because the field around this is changing, that's going to induce current in this one, the secondary one, okay? Now this property here, the metal here, helps to let the field get in properly, or the flux get into the secondary distance properly. Now sometimes circular currents can be set up in this one. That circular current is what we call eddy current, okay? Eddy current. They usually will lead to heat production. So they are usually not desired. So sometimes what you do is that you need to separate them or make holes in it so that you cut off, you reduce the amount of eddy current that will be made. Now from this principle, the EMF that will be generated, let's say EMF of the secondary, the secondary is proportional over EMF of the primary, is proportional to the turns in the secondary, then the turns in the primary. This is what I want us to look at. The number of coils here will correspond to the current that will be produced. So this is proportional to this is this, and this is that. The ratio between this and that, the E2 and E1 is the same as the number of turns, okay? So, I mean, if you have more turns here, then more turns here than here, then the ratio will stand as it is. So depending on how many turns you have, the ratio is set up as this. So this is to say that if you want this one to be more, then the number of coils should be more, so that I can get more current in there. It's kind of setting up, rather. So the same, the reverse will be true. So depending on what kind of transformer is being used, either you are beating up the current or beating it down. So that is that for transformer. We'll move on to the next one. The speedometer, of course, we have said, also works by the method of electromagnetic induction. So the speedometer also works by the method of electromagnetic conduction. So that means we have, for it to move, then we should have current. Two currents, two fields interacting, okay? So let's move on let's look at some properties of the solenoid or the inductor. Then we will look at AC currents, and that will bring us to the end of the discussion. Then it will bring us to the end of the discussion. All right, so let's look at this one, the inductor. Okay, so the inductor, what the inductor does is to store energy in a form of magnet. So to store energy in a form of magnet. So if you have the coil, the solenoid, so current comes, goes away and away. Okay, so this sets up sort of a field, a changing field, each around each other, each around the other. Okay, and then we have a magnet which is set up. A magnetic field is set up. Okay, so this is a solenoid, and that's if a magnetic, if let's say you have a conductor in here, the magnetic field setup can draw something, as in the case of the alarm bells or the gate bells. Okay, drawing. Now the inductor, what the inductor does is to convert electricity or current to magnetic field. Okay, so the energy is stored in the form of magnetic field. Okay, right. Now it's as a result of the electrons moving, set up magnetic field. So that is, their movement is converted to a magnetic field. So the EMF that is set up, that EMF is what we call back EMF. It's called back EMF because it tends to oppose the one which was inducing it, and that is proportional to the rate of change of current. Rate of change of current. Let's note that the rate at which current was changing will be proportional. The EMF will be, the back EMF will be equal to that. So the back EMF will be equal to K change of this. Okay. But this K happens to be what we define as the inductance of the conductor you are dealing with. So E will be proportional to this over T. Right. Of course, this is a kind of a back. So this is one equation you can look at. Okay, so if you know the current, the rate at which current is changing, and then you know the inductance of, so this, you know the rate at which current is changing within this. Okay, and then you know the inductance of this material, then you can calculate how much EMF will be generated. That is it. Okay, so the inductor is similar to the conductor. Okay, the two can be put in together in radius. Okay, so that the current usually, in the case of the conductor, it takes time for the charge to build to create a voltage. So you will see that in the case of conductor, the current leads the voltage. In the case of the inductor, immediately you set up, you close the circuit, the voltage in the inductor is set up, okay, for current to flow. So voltage will lead inductor. This principle is very important. We will need it in when we are calculating for AC parameters, the AC alternating current parameters. Alright, so that is one thing I want us to note, okay? And this is another formula you can keep in mind. The induced or the back EMF is given by this principle. Now, the formula for the work done by the energy stored in the inductor is equal to half L I squared. Okay. Okay. So if it is alternating current, this is it. This is the formula, the work done. This can be deduced, okay, from the work done formula. That work done is equal to force times distance. Okay. Then this you can look at it. This is your EMF. So your EMF, and of course, we say that the energy is also the same as what your charge times your voltage, or which is the same as your charge, this energy times your E. If you put your E here, in place of this, you put your E here, okay? And then you substitute for, what do you call it? You make, what do you call it, time for other factors. Let's see how the equation will roll out. That's what we're going to look at next. Let me just clean this part. Right, so we have the formulas as such. So this is now inductor we are talking about. Let's put it on the board. So we are looking at the current that has gone in to set up a magnetic field as energy. Okay, what is called the back EMF. Right. Now we are saying that we want to find the work done. Work done will be equal to, so if we had, let's say, the energy here, the voltage, this is the EMF, the voltage, against the charge, which is current. Okay. If you have a plot like that. Right. Let's see, so if we sum this one over the T, so that this becomes the Q, and this is E, then work done will be equal to summing the E and then multiplying by the Q. Okay? Right. If you sum the E and you multiply by the Q, you should get the answer, because we said work done is equal to what? Charge times what? Voltage. Okay? So here is the EMF which is there. We want to find the energy in the inductor. Okay? So this we can sum up E, we know is equal to, is defined by what? The rate L, the rate of change of what? T. Okay, and then we also know that E is also equal to the flux change of T. This one, we'll look at it later. Okay, so if we substitute this, of course, we also know that the Q over the T is equal to I, which implies the Q is equal to I dt. Okay, so if we are substituting this for that, and then this for this, okay, so that we want to get the current. Is the current that we have an idea. So if you know an equation related to the current, then we can work things out. So that this becomes integrating L di dt times the times what? I dt. And then you have the Q here. So the Q has been replaced. Okay, so that's it. So from here we have substituted for this and that. This will cancel this, so that we have L is a constant, so L comes out. Okay, then we have I coming, we have the I here. Okay, so integrating from the current, from the point, from the initial to the final, okay, it gives us the equation. So when you do that, what do you think will be the answer? We can do the integration. If you integrate this one, we're going to get what? I 1 plus 1 divided by 2. Okay, right? From 0 to final I, this L. Okay, so this comes out as half. This is the max. Okay, this is going to be 0. So half what? L. This becomes 2. I half L I 2. So this is the formula that we are looking at. So the final minus the initial, which is 0. Okay, that's what we are looking at. This is over 2. Alright, so this is the equation. That's work done is equal to half L I 2. Remember the work done for capacitor. Work done for capacitor was what? Half. That we did the equation for. Then Q, you can check out for, and it was related to another factor. You can check that one out from the first equation. If you've forgotten, go back to the same principle where we say Q. I always say that you can always get the equation once you know how to work things out. Okay? So if you've forgotten the capacitor, for the capacitor is what? Integration of, or let's say, is Q times what? Voltage. Okay? But the voltage goes from 0 through to the final V. Okay, so the average of this is half. So that's a half voltage, half voltage, and then maximum charge. Okay, something like that. So that's the way done for the capacitor. Okay, you can substitute for C and I and so on into the equation. Okay, where you'll be getting the space. Okay, so the same thing here. This is what we have. Right. So let's look at an arrangement here. Right, so let's look at this. Now, let's say this is a current carrying conductor. Okay, it has a varying current in it, and so that therefore the current around it, the field is also changing. So far as the field is changing, it will interact. That field is a domain. It's a domain of electrons. So it will interact with the electrons in this and then cause separation for an EMF to be set up. Okay, this EMF that is set up will be proportional to the rate at which the current was changing. Now we have something we call the mutual inductance or mutual inductance. Okay, this EMF will be equal to a constant times changing the rate at which the current was changing. This E is what we call the mutual inductance constant. Okay, so E becomes that. This is the formula I wanted us to come up with. In essence, right, so let's look at the same principle. Now, the EMF is also what is induced in this one. The flux, let's say this is B, this is A. The flux, so this one is in A, so this is in B. What has been induced in B? EB is also equal to the flux that has changed here, flux in B. The rate at which this flux is changing. This flux in B is changing. Okay, it's also equal to the rate at which this flux is also changing is proportional to your induced B. Right. So so this is the rate, and this is, we have said this is equal to the I, where I is the current in A, okay, dt times what, M. So we realize that from here, this cancels that, okay, and then we can see from here, if you integrate this one, you're going to get flux B, and integrate this part, you're going to get what, M times what, IE. Okay, this is another relation. Okay, so always picture it like that. Okay, and then this will help you to get the picture when you are dealing with the questions. Okay, right. M is found to be proportional to L1, L2. Okay. Where L1 and L2 are the respective inductance. So inductance of this is inductance of this ability to convert the current to magnetic energy. The same thing, the ability to convert current energy to magnetic energy is also given as that. Right. So this is an equation that you should also look at. Right. So at this point, I think we have exhausted the magnetic part of the equation. We will move to the AC current. So let's briefly look at the, now when we're doing this for the coil, then we have magnetic here. Okay, this is a coil, but where, and then this was generating this, so this is the generator. Okay. Now if this happens to be what you call the homopolar. Homopolar. This one is a disk. Okay. If it is a disk which is moving round rather, then what will happen is at the end, the current that is generated will move in the same direction. It's not going to be AC. So you have a steady kind of current generated if this is this. Okay. Right. So that is what I wanted to point out. If you look at it from